1 light year. It sounds like the smallest useful distance between stars. Astronomers toss the phrase around as casually as miles on a highway. But here is what nobody tells you. If you climbed aboard the fastest machine humanity has ever built, a spacecraft that set its speed record on Christmas Eve 2024 by screaming past the sun at 692,000 kilometers per hour, and if you pointed it toward open space and never stopped, you would still be flying for more than 1,500 years before you crossed that single light year. And 1 light year does not even get you a quarter of the way to the nearest star. This is the distance that breaks everything we think we know about travel. If you want to understand why the smallest ruler line between the stars is already enough to humble every machine we have ever launched, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. The phrase sounds harmless. 1 light year. Say it out loud and it almost feels manageable, as if a light year were some kind of modest cosmic step, the interstellar equivalent of a long highway drive. People hear the word 1, and their brains latch onto the smallness of the number. 1. A single unit. How intimidating can a single anything really be? This is where the trap closes. A light year is not a measure of time. This is the most widespread misunderstanding in all of popular astronomy, and it poisons nearly every casual conversation about how far away things are. The word year, sitting inside the phrase, convinces people that a light year describes how long something takes. It does not. A light year is a measure of distance. Specifically, it is the distance that light, the fastest phenomenon permitted by the laws of physics, manages to cross during 1 full year of continuous, uninterrupted travel. Light does not slow down in a vacuum. It does not pause, coast, or lose momentum. It travels at exactly 299,792 kilometers per second, every single second, without deviation. A light year is what you get when you let that speed run non-stop for 365.25 days. The result is a number that sounds clinical until you try to feel its weight. 1 light year equals approximately 9.46 trillion kilometers. Written out in full, that is 9,460 billion kilometers. Or if you prefer miles, roughly 5.88 trillion of them. These are numbers that the human brain cannot process in any meaningful way. You can read them, you can say them aloud, but you cannot picture them. No person who has ever lived has possessed the neurological hardware to genuinely visualize what trillions of anything look like, let alone trillions of kilometers stretching in a silent line through the emptiness between stars. And yet, astronomers treat 1 light year as if it were the smallest useful unit on the interstellar measuring tape. They have to. The distances between stars are so extreme that using kilometers would be like measuring the width of an ocean in millimeters. Technically accurate, hopelessly impractical, the light year exists because the cosmos demanded a bigger ruler. But what most people never realize is that even this bigger ruler, even this single unit that astronomers invented to make the universe comprehensible, already contains more distance than humanity has come close to conquering. To understand what 1 light year actually means, you have to start with what light does on scales you can almost relate to. Right now, at this exact moment, photons are leaving the surface of the sun and racing toward Earth. Those photons are moving at 300,000 kilometers every second. They cross the void between our star and our planet in approximately 8 minutes and 20 seconds. Think about what that means. The sunlight warming your skin left the sun about 8 minutes ago. If the sun vanished right now, you would not know for another 8 minutes. For 8 minutes and 20 seconds, Earth would keep orbiting a star that no longer existed, illuminated by ghost light from a dead source. That 8-minute gap represents about 150 million kilometers, a distance astronomers call 1 astronomical unit. It is the foundational yardstick of our solar system, the baseline from which every other planetary distance is measured. 1 astronomical unit is already an enormous distance by any human standard. If you could drive a car at highway speed toward the sun, the trip would take roughly 170 years. No human lifespan would survive the commute. Yet this distance, this seemingly impossible stretch of 150 million kilometers, represents an almost vanishing fraction of 1 light year. 1 light-year contains approximately 63,241 astronomical units. The distance from Earth to the Sun, multiplied 63,000 times and laid end to end in a straight line, still falls slightly short of a single light-year. Let that comparison settle. The Sun-Earth gap, a distance so vast that light itself needs over 8 minutes to cross it, must be repeated more than 63,000 times before you have measured 1 light-year. And 1 light-year is what astronomers consider the starting unit for interstellar distances. Now follow the light outward through the solar system and watch how the numbers grow. After 8 minutes, sunlight reaches Earth. After about 13 minutes, it crosses the orbit of Mars. In 43 minutes, it reaches Jupiter. In roughly an hour and 20 minutes, sunlight arrives at Saturn. After roughly 2 hours and 40 minutes, it passes Uranus. And after approximately 4 hours and 10 minutes, it reaches Neptune, the outermost major planet in our solar system. Keep going. After roughly 5.5 hours, sunlight reaches the average distance of Pluto. 5.5 hours for the fastest thing in the universe to travel from the center of our solar system to its most famous dwarf planet. That distance is about 40 astronomical units, 40 copies of the Sun-Earth gap. And at this point, light has covered less than 1,000th of 1 light-year. The math is unforgiving. Light needs 5.5 hours to reach Pluto. It needs a full year to cross 1 light-year. That means the distance from the Sun to Pluto fits inside 1 light-year more than 1,500 times. You could stack the entire Sun to Pluto distance end to end 1,500 times, and you would just barely have assembled 1 light-year. The solar system that feels so immeasurably huge to us, this enormous arrangement of planets and moons and asteroid belts and comets that took humanity thousands of years to even begin mapping, turns out to be a speck inside the distance that astronomers treat as a single rung on the cosmic ladder. But the solar system does not actually end at Pluto. Not even close. Beyond the orbit of Neptune and the scattered disk of icy bodies that includes Pluto, there exists a vast, dark, and almost entirely unexplored region that most people have never heard of. The Oort cloud. This is a theoretical shell of trillions of icy objects, frozen remnants from the formation of the solar system, drifting in the outermost gravitational grasp of the Sun. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 astronomical units from the Sun. Its outer boundary may extend as far as 100,000 astronomical units outward, which translates to somewhere between 1 and 2 light-years from our star. Hear that again carefully. The Oort cloud, which is still considered part of our solar system because its objects are still gravitationally bound to the Sun, extends to roughly 1 or even 2 light-years from the center of that solar system. This means that when you say you want to travel 1 light-year, you may not even be talking about leaving the Sun's domain. You may still be inside the loosest, coldest, most remote outskirts of our own star's gravitational influence. 1 light-year might not get you out of the solar system. It might only get you to the edge of the Sun's gravitational farewell, the boundary where our star's pull finally becomes too weak to hold on to the frozen debris orbiting in eternal slow motion. This realization changes the entire picture. 1 light-year is not a distance that launches you into the universe between the stars. It is a distance that might only barely separate you from the star you already know. The interstellar medium, the true void between stellar systems, begins at the outer edge of the Oort cloud. If that edge sits at 1 or 2 light-years from the Sun, then 1 light-year is not an interstellar journey at all. It is the distance required to reach the fence at the end of your own backyard. And here is where the phrase 1 light-year reveals its most brutal deception. People assume that 1 light-year gets you meaningfully closer to another star. It barely moves the needle. The nearest known star system to our Sun is Alpha Centauri, a triple star system whose closest member, Proxima Centauri, sits approximately 4.24 light-years from Earth. 1 light-year covers less than a quarter of that distance. Not half, not a third, less than a quarter. You would need to cross 1 light-year, then do it again, then do it again, and then travel most of a 4th light-year before you reach the closest star that is not our own Sun. To make this concrete, imagine the distance between the Sun and Proxima Centauri as a road stretching from New York City to Los Angeles. 1 light-year would get you to roughly eastern Tennessee. You would have crossed the Appalachian Mountains and entered a new time zone, and you might feel like you had covered serious ground. but the Pacific Ocean would still be impossibly far ahead. The vast majority of the journey, more than 3/4 of it, would still remain, and this is the nearest star. Most stars visible to the naked eye are hundreds or thousands of light years away. The center of our galaxy is roughly 26,000 light years from Earth. The nearest large galaxy, Andromeda, sits 2.5 million light years away. At those scales, 1 light year does not even register as a meaningful distance. The reason this matters so deeply is that people routinely underestimate interstellar distances by conflating light years with something familiar. They hear that Proxima Centauri is 4.2 light years away and think it sounds close, as if it were a few towns over. What they do not realize is that each of those 4.2 units contains 9.46 trillion kilometers of hard vacuum, radiation, micrometeorites, and absolute silence. 4.2 light years is not 4.2 of some friendly, manageable quantity. It is 4.2 repetitions of a distance so vast that it humbles every vehicle humanity has ever constructed. But 1 light year does something even more insidious to human understanding. It hides the true gap between planetary travel and interstellar travel. Humanity has sent spacecraft to every planet in the solar system. We have landed machines on Mars, dropped probes into the atmosphere of Jupiter, and flown past Pluto. These achievements are extraordinary, and they span distances of billions of kilometers. The Voyager missions have been traveling for nearly 50 years and have reached roughly 170 astronomical units from the Sun. That distance sounds impressive until you measure it in light years. 170 astronomical units equals approximately 0.0027 light years. After half a century of continuous flight at tens of thousands of kilometers per hour, Voyager has covered less than 3/1000 of a single light year. This is not a gentle incline from planetary distances to interstellar distances. This is a cliff. The difference between the farthest any human machine has traveled and the distance of 1 light year is not a factor of 10 or a factor of 100. It is a factor of thousands. Everything humanity has accomplished in spaceflight, every mission, every record, every gravity assist and engine burn and trajectory optimization across 6 decades of space exploration adds up to a fraction so small that it essentially rounds to 0 on the interstellar scale. The light year was invented because the distances between stars demanded a unit large enough to make the numbers fit on a page, but the act of giving that distance a tidy name created a cognitive illusion. When something has a short pronounceable label, the mind assumes it describes something comprehensible. People can visualize a kilometer because they have walked one. People can feel a mile because they have driven one. Nobody has ever experienced a light year. Nobody has ever stood at one end of a light year and looked across to the other side. The label exists purely as mathematical shorthand, and it tricks the brain into thinking it has grasped the concept when it has grasped only the word. Consider what is actually contained within that single light year. If you could somehow freeze the space inside 1 light year and examine it, you would find almost nothing. A few stray hydrogen atoms per cubic centimeter, occasional wisps of interstellar dust, particles smaller than the width of a human hair, scattered across distances so enormous that you could travel for years without encountering a single one. Faint traces of cosmic radiation left over from ancient stellar explosions, and nothing else. No landmarks, no reference points, no visible change from 1 trillion kilometers to the next. The interior of a light year is the purest, most absolute emptiness that nature is capable of creating. It is not the emptiness of an unoccupied room or an unused field. It is the emptiness of a vacuum so thorough that individual atoms are separated by distances that would require a microscope to cross on Earth but stretch for millions of kilometers in open space. Flying through this emptiness would be unlike any journey a human being has ever experienced. There would be no sensation of progress, no scenery changing outside the window, no mileposts ticking past. If you left the solar system headed for a 0.1 light year away, you would see the sun growing dimmer behind you over the course of years, shrinking from a blazing disk to a bright star to a faint point among thousands of other faint points. Ahead of you, nothing would change. The stars would remain fixed in their positions because even at tremendous speed, 1 light year is too short a distance to produce any noticeable shift in the stellar background. You would feel motionless. The universe would appear frozen around you, Only the steadily fading sun behind you would confirm that you were moving at all. And this motionless feeling would persist for an almost inconceivable amount of time. At speeds humans have actually achieved, crossing 1 light year requires not decades, not centuries, but millennia. The fastest outward-bound spacecraft in history would need more than 17,000 years to travel 1 light year. The fastest speed any human machine has ever reached, a record set in orbit around the Sun rather than in interstellar cruise, would still require more than 1,500 years. These are not engineering problems that a better engine might fix. These are consequences of a distance so large that it exists in a fundamentally different category than anything humanity has encountered before. The gap between our fastest machines and the distance of 1 light year is not a challenge. It is a wall that most people do not even know is there, because the phrase 1 light year sounds so small. But knowing the distance is only the first shock. The real devastation begins when you try to cross it. When you take the fastest machines humanity has ever launched, point them at open space, and calculate how long the trip would actually take. That calculation is where 1 light year stops being a number on a page and starts being a verdict on human capability. What comes next turns that verdict into something almost unbearable. The fastest object humanity has ever aimed at the outer solar system left Earth on September 5, 1977. Voyager 1 launched aboard a Titan IIIe Centaur rocket, received gravity assists from Jupiter and Saturn, and has been coasting through space ever since. It carries no engine that can fire again. It has no fuel left for significant acceleration. It simply drifts at the velocity those planetary flybys gave it nearly 5 decades ago. And it is the most distant human-made object in existence. As of 2026, Voyager 1 is approximately 25.5 billion kilometers from Earth. That distance is roughly 170 astronomical units. It has taken 49 years of continuous flight to reach that point. Signals from the spacecraft, traveling at the speed of light, now require approximately 23 hours to reach the mission control antennas on Earth. In November of 2026, Voyager 1 is expected to reach a remarkable milestone. It will be 1 light day from Earth, the distance that light itself covers in 24 hours. 1 light day, after half a century. Let that sink in before the real calculation arrives. There are 365.25 days in a year. 1 light year contains 365.25 light days. Voyager 1 has been flying for nearly 50 years and has covered approximately 1 light day. At that pace, crossing a full light year would require roughly 18,000 years. More precise calculations using the spacecraft's actual velocity of approximately 17 kilometers per second produce an estimate of about 17,600 years. 17,600 years to cross 1 light year using the fastest interstellar-bound machine humanity has ever built. To understand what 17,600 years means in human terms, consider that recorded civilization is only about 5,000 years old. The oldest known writing systems appeared in Mesopotamia around 3000 CE. Every empire that has risen and fallen in human history, every dynasty, every revolution, every technological age from bronze to iron to steam to silicon, all of it fits within those 5,000 years. Voyager 1 would need roughly 3.5 times the entire duration of recorded history to cross a single light year. When it finally arrived, assuming it survived that long, which it absolutely would not, the humans who launched it would be as ancient and forgotten as the civilizations that built the first stone tools. And Voyager 1 is moving fast by any standard that makes sense on Earth. 17 kilometers per second translates to about 61,000 kilometers per hour, or roughly 38,000 miles per hour. At that speed, you could circle Earth's equator in less than 40 minutes. You could travel from London to Sydney in about 20 minutes. Voyager is not crawling through space. By the standards of any vehicle ever used on this planet, it is screaming through the void at a velocity that would be lethal if anything stood in its path. But the interstellar scale does not care about earthly standards. At 17 kilometers per second, Voyager 1 covers roughly 530 million kilometers per year. That sounds enormous until you remember that 1 light year is 9.46 trillion kilometers. Dividing the light year distance by the annual distance covered produces the same crushing number, roughly 17,600 years. No matter how you frame the arithmetic, the answer stays the same. What makes Voyager's position even more sobering is what the spacecraft has actually experienced since it crossed the boundary of the Sun's direct influence. In August 2012, Voyager 1 officially entered the interstellar medium. It became the first human-made object to leave the heliosphere, the enormous bubble of charged particles that the Sun blows outward into space. Inside the heliosphere, the solar wind dominates. Charged particles stream outward from the Sun at hundreds of kilometers per second, creating a protective cocoon around the entire solar system. This cocoon deflects much of the galactic cosmic radiation that permeates interstellar space. It is, in a very real sense, the Sun's atmosphere extended across billions of kilometers. When Voyager crossed the heliopause, the boundary where the solar wind finally loses its battle against the pressure of the interstellar medium, everything changed. The density of plasma around the spacecraft increased dramatically. The character of that plasma shifted from hot, fast solar particles to cooler, denser interstellar material. Cosmic ray detections jumped. For the first time, a human instrument was directly sampling the environment between the stars, and what it found was emptiness of a different character than the emptiness within the solar system. Inside the heliosphere, you are surrounded by the Sun's influence. Particles carry the Sun's magnetic signature. The solar wind pushes against everything. There is a directionality to the environment, a sense that something powerful is nearby. Outside the heliosphere, that directionality vanishes. The interstellar medium is calm, cold, and directionless. It has no center. It answers to no single star. It is the default state of the galaxy, the backdrop against which solar systems exist as tiny temporary disturbances. Voyager confirmed this transition with data, not theory. The plasma wave instrument detected vibrations in the interstellar medium that allowed scientists to measure its density. The cosmic ray detectors registered a sharp increase in galactic cosmic rays, the high-energy particles that originate from distant supernovae and other violent events across the galaxy. The solar wind, which had been a constant presence for 35 years of flight, dropped to near zero. Voyager had left home. But what it found in interstellar space was not silence. It was something stranger. Beginning shortly after crossing the heliopause, Voyager 1's plasma wave instrument began detecting a faint, persistent signal, a narrow-band oscillation in the electron plasma surrounding the spacecraft. Scientists initially noticed it between the bursts of activity caused by shock waves from solar eruptions, coronal mass ejections that ripple outward from the Sun, and eventually wash through the interstellar medium months or years after the eruption. Between those solar-driven events, when the plasma returned to its undisturbed state, the same faint vibration appeared. Steady, continuous, unchanging. Researchers described it as a hum, not a sound that any human ear could hear, but a persistent oscillation in the density of interstellar electrons, vibrating at a frequency determined by how many charged particles occupied each cubic centimeter of space. The frequency was tiny, measured in thousands of oscillations per second, and the signal was extraordinarily faint. But it was real, and it was everywhere. Whenever the disturbances from our Sun faded and the interstellar medium settled into its resting state, the hum returned. This discovery, published in 2021, gave scientists something remarkable, a continuous measurement of the baseline density of interstellar space. By tracking the frequency of the hum over time, researchers could monitor how dense the surrounding medium was at each point along Voyager's path, producing a density profile of interstellar space that no observatory on Earth could have obtained. The measurements showed the local interstellar medium hovering at a density of roughly 0.05 to 0.12 electrons per cubic centimeter. That is astonishingly thin. The air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The interstellar medium contains a fraction of one particle in the same volume. But the hum itself is what lingers in the imagination. It is the sound of the galaxy doing nothing, the acoustic fingerprint of the void at rest. When no star is erupting, when no shockwave is passing through, when nothing at all is happening in a region of space, trillions of kilometers from the nearest star, this faint vibration is all that exists. It is the resting heartbeat of the emptiness that fills the interior of every light year. It is what a spacecraft crossing 1 light-year would hear, if hearing were possible, for thousands of years. The same frequency, the same faint tremor, unchanging and endless. Voyager detected this because it is there, drifting through the galaxy's background medium at 17 kilometers per second. It is the first and so far the only human instrument to listen to the silence between the stars and discover that it is not quite silent. The void hums, faintly, constantly, and without variation, across distances so vast that nothing else happens at all. If you were aboard a spacecraft crossing 1 light-year, this hum would be your constant companion, not heard through the hull, but registered in every instrument reading, every plasma diagnostic that sampled the space outside your vessel. Year after year, the same faint oscillation, no change in pitch, no variation in strength, no interruption except the occasional distant echo of a solar eruption from a star you could no longer see. The frozen stars ahead, the featureless void in every direction, would be joined by this acoustic monotony. Not silence, but something lonelier than silence. A single unchanging note sustained across trillions of kilometers, confirming that the space you are crossing contains almost nothing, and that the nothing stretches farther in every direction than your instruments can reach. The hum would not grow louder as you traveled. It would not shift as you crossed from one region of interstellar space to the next. It would simply persist, unchanged, for as long as your instruments survived to detect it. But here is the part that matters for the question of 1 light-year. Voyager crossed the heliopause at roughly 121 astronomical units from the Sun. That is about 0.0019 light-years, less than 2/1000ths of 1 light-year. The boundary of the Sun's active influence, the edge of the protective bubble that shields every planet in our solar system from the full force of galactic radiation, sits at less than 2/1000ths of the distance we are trying to cross. Voyager travelled for 35 years to reach that boundary. It has now spent another 14 years beyond it, and its total distance from the Sun still amounts to barely more than 1/4% of a single light-year. The interstellar medium that Voyager entered is the same material that fills the entire interior of a light-year. Thin hydrogen gas, faint magnetic fields from distant sources, cosmic rays arriving from every direction. A persistent hum in the electron plasma so faint it required the most sensitive instrument on a spacecraft, 25 billion kilometers from Earth, to detect it. Almost no structure, almost no variation, almost no feature that a spacecraft could use to mark progress. Voyager is sampling the same void that any interstellar traveler would spend thousands of years crossing, and it is doing so at a speed that makes the crossing essentially impossible. Voyager 1 is not alone out there. Its twin, Voyager 2, launched the same year and travelled a different route through the outer planets. It moves slightly slower, at about 15.4 kilometers per second relative to the Sun, and would take roughly 19,400 years to cover 1 light-year. Voyager 2 crossed the heliopause in November 2018 at a distance of about 119 astronomical units, confirming that the heliosphere's boundary varies in different directions. It too now drifts through the interstellar medium, sending back data that largely confirms what Voyager 1 reported. Cold, quiet, empty space. New Horizons, the spacecraft that famously flew past Pluto in 2015 and later visited the Kuiper Belt object Arrokoth, currently cruises at about 14 kilometers per second. Its light-year crossing time would exceed 21,000 years. As of 2024, it passed 60 astronomical units from the Sun, meaning it is still deep inside the heliosphere, not yet even close to the boundary that the Voyagers crossed decades ago. These are not rough guesses. These are straightforward calculations that any student with a calculator can verify. Distance divided by speed equals time. The formula is elementary. The result is devastating. 3 spacecraft, representing 6 decades of propulsion engineering and trajectory design, all coasting through space at speeds between 14 and 17 kilometers per second. The fastest among them needs more than 17 millennia to cross 1 light-year. The slowest needs more than 21 millennia, and all 3 are gradually losing power. Their radioisotope power sources decay a little more each year. Voyager 1 has already had most of its instruments shut down to conserve electricity. In 2025, engineers shut down the cosmic ray subsystem, the very instrument that had confirmed the crossing into interstellar space. Within the next few years, it will fall silent entirely, drifting through the dark without any ability to communicate, observe, or report. Long before it reaches 1 light year from the Sun, it will be nothing more than a dead metal capsule carrying a golden record that no one may ever play. But there is another spacecraft that appears to change the equation dramatically. On Christmas Eve, 2024, the Parker Solar Probe achieved the fastest speed ever recorded by any human-made object. At the closest point in its orbit around the Sun, known as perihelion, the probe reached 192 kilometers per second. That is 692,000 kilometers per hour, roughly 430,000 miles per hour. At that velocity, you could fly from Earth to the Moon in about 33 minutes. You could reach Mars at its closest approach in roughly 3.5 days. The number sounds like a breakthrough. 192 kilometers per second is more than 11 times the speed of Voyager 1. If you divide the distance of 1 light year by this speed, you get a travel time of approximately 1,560 years. Compared to Voyager's 17,600 years, 1,560 years sounds almost reasonable. Still long, but closer to the timescales of known civilizations rather than the timescales of geological epochs. Except it is a mirage. Parker Solar Probe does not and cannot maintain 192 kilometers per second on a trajectory away from the Sun. That record speed exists only at perihelion, the moment when the probe is closest to the Sun, falling through the star's gravitational well on a tightly curved elliptical orbit. Think of a ball rolling into a steep bowl. At the bottom of the bowl is moving at maximum speed, but it does not keep that speed. It climbs back up the other side, slowing down as gravity pulls it back. Parker behaves the same way. It screams through its closest solar approach at record velocity, then climbs away from the Sun on the outbound leg of its orbit, losing speed with every passing hour. Parker was never designed for interstellar travel. It was built to study the Sun's outer atmosphere. Its entire mission depends on repeatedly diving close to the Sun and pulling away over and over, collecting data on the solar corona and solar wind. The spacecraft is trapped in orbit around the Sun. It will never leave the solar system. It will never head for the stars. Its record speed is a product of solar gravity, not propulsion technology. No engine carried Parker to 192 kilometers per second. The Sun's own mass did the work, accelerating the probe during its plunge toward perihelion. If you took a spacecraft identical to Parker and somehow pointed it away from the Sun at 192 kilometers per second, 2 problems would immediately appear. First, the Sun's gravity would begin decelerating the craft the moment it started heading outward. Without the Sun's gravitational pull maintaining that orbital speed, the probe would slow down steadily as it climbed out of the Sun's gravity well. By the time it reached the outer solar system, its velocity would be far lower than 192 kilometers per second. Second, no existing propulsion system could achieve that speed in the first place without using solar gravity. Chemical rockets, ion drives, and every engine ever tested by a space agency would fall far short. This distinction between orbital speed and escape speed is critical. It is the difference between a roller coaster reaching top speed at the bottom of a drop and a car reaching top speed on a flat highway. The roller coaster is fast because gravity is pulling it downhill. The car is fast because its engine is pushing it forward. One speed depends on a hill that cannot be carried along. The other depends on sustained power. Interstellar travel demands sustained power, or at least a single enormous push sufficient to reach a speed that can be maintained across trillions of kilometers. Parker's record provides neither. The actual escape speed that a spacecraft can sustain after leaving the solar system is a far more honest number. Voyager 1's 17 kilometers per second is approximately what an outward-bound spacecraft can realistically carry into interstellar space using current technology. That is the number that matters. That is the speed that determines how long the trip actually takes. And that speed is astonishingly small compared to light. Put the numbers side by side. Light travels at 299,792 kilometers per second. Voyager 1 travels at 17 kilometers per second. The ratio is approximately 1 to 17,600. Voyager is moving at roughly 0.0057% of light speed. Not 5%, not 0.5%, 0.005%. Even Parker's record perihelion speed of 192 kilometers per second is only 0.064% of the speed of light, less than 0.1%. The fastest thing humans have ever built, at the absolute peak of its velocity in the most favorable gravitational conditions possible, reaches less than 0.1% of light speed. These percentages matter because they reveal the true scale of the gap. When people hear that light crosses 1 light year in 1 year, they subconsciously assume that human spacecraft must be some meaningful fraction of that speed. 10% maybe, 5% at worst. Surely we have closed part of the gap after 7 decades of spaceflight. We have not even close. Human propulsion technology does not occupy the same scale as light speed. It does not sit at the bottom of a ladder that light sits atop. It is standing in the parking lot outside the building where the ladder is stored. The gap between 17 kilometers per second and 300,000 kilometers per second is not a challenge that can be described in terms of percentage points. It is a gap of 4 entire orders of magnitude, a factor of almost 18,000. What does that factor feel like in real terms? Consider an analogy using time. If 1 light year of travel at light speed takes 1 year, then traveling at Voyager's speed converts that same distance into 17,600 years. Now imagine some everyday activity that takes you 1 year. Perhaps you are growing a garden from seed to harvest. At Voyager's proportional slowness, that same garden would need 17,600 years to grow. You would plant the seed during the last ice age and harvest the tomato in the present day. Or think of it this way: a commercial aircraft crosses the Atlantic Ocean in about 7 hours. Now slow that aircraft down by the same factor that separates Voyager from light speed. Instead of 7 hours, the Atlantic crossing would take roughly 14 years. You would board the plane as a young adult and land as a middle-aged parent. The aircraft would be technically functional, technically moving, technically making progress across the water, but the progress would be so slow relative to the distance that the journey would consume a significant portion of your entire life. This is the speed gap. Not a gap you can close with cleverness or incremental improvement. A gap so wide that it transforms 1 year of travel into millennia. A gap that converts the phrase 1 light year from a tidy unit of astronomical distance into a prison sentence for any machine constrained to current speeds. Some people respond to these calculations by pointing out that technology improves. Speeds that seemed impossible a century ago are routine today. The first powered aircraft flew at about 48 kilometers per hour. Modern spacecraft travel at tens of thousands of kilometers per hour. Is it not reasonable to expect that speeds will continue climbing until they approach some useful fraction of light speed? The answer is more complicated than it first appears. It is true that spacecraft speeds have increased since the dawn of the space age, but the rate of increase has been slowing, not accelerating. The jump from 0 to the first orbital velocities in the 1950s was dramatic. The further jumps from orbital speed to planetary flyby speed to outer solar system escape speed were significant. But since the Voyager missions launched in 1977, the escape speeds achievable by outward-bound spacecraft have not changed dramatically. New Horizons launched nearly 3 decades after Voyager, with the benefit of a much more powerful rocket, and achieved a faster departure speed from Earth. But after its Jupiter gravity assist, its cruise velocity ended up slower than Voyager 1's. Better rockets did not translate into faster interstellar travel. The fundamental reason is energy. Speed is not free. Every additional kilometer per second of velocity demands energy, and the energy required grows with the square of the speed. Doubling your speed requires 4 times the energy. Tripling it requires 9 times. Reaching 1% of light speed, roughly 3,000 kilometers per second, would require accelerating a spacecraft to a velocity 176 times faster than Voyager 1. The energy needed for that acceleration scales with the square of that factor. You would need approximately 31,000 times more energy than the missions that launched Voyager. For a craft the mass of Voyager, That energy is roughly equivalent to the output of a large power plant running for a year, all concentrated into a single act of acceleration. And 1% of light speed still produces a 1 light-year crossing time of 100 years, better than 17 millennia, certainly. But still a full human century during which the spacecraft must survive the vacuum, endure radiation, maintain communication, and avoid catastrophic impacts with interstellar debris. But there is a deeper reason why bigger rockets have not produced faster interstellar speeds, and it reaches all the way down to the fundamental mathematics of how rockets work. A rocket moves by throwing mass out of its back end. The faster it throws that mass, the more efficiently it gains speed. The speed at which exhaust leaves a rocket engine is called the exhaust velocity, and this single number determines the theoretical ceiling for how fast any rocket can go. Chemical rockets burn hydrogen and oxygen and produce exhaust velocities of roughly 4 to 4.5 kilometers per second. This is an absolute limit set by the chemistry of combustion. No chemical reaction between any known propellants can produce significantly faster exhaust. Now here is where the mathematics becomes merciless. The fundamental equation of rocketry, derived in the late 19th century, relates a spacecraft's final speed to the exhaust velocity of its engine and the ratio between the spacecraft's initial mass, fully loaded with fuel, and its final mass after all the fuel has been burned. The relationship is logarithmic. To reach a speed equal to the exhaust velocity, a rocket must start with about 2.7 times more fuel than payload. To reach twice the exhaust velocity, the ratio climbs to about 7.4. 3 times the exhaust velocity requires a ratio of about 20. 4 times requires 55. 5 times requires about 148. The numbers escalate with vicious speed. To reach 10 times the exhaust velocity, a chemical rocket would need a fuel-to-payload ratio of more than 22,000. That means for every kilogram of spacecraft that arrives at its destination, 22,000 kilograms of fuel must be loaded at departure. For a spacecraft the mass of Voyager, roughly 800 kilograms, you would need more than 17 million kilograms of fuel. That is heavier than most ocean-going cargo ships. And 10 times the exhaust velocity of a chemical rocket is only about 45 kilometers per second, roughly 2.5 times the speed of Voyager. Still, nowhere near 1% of light speed. Still a crossing time measured in thousands of years per light year. This is why simply building a bigger rocket does not work. The rocket equation punishes ambition exponentially. Every additional kilometer per second of desired speed demands not a little more fuel, but vastly more fuel. The fuel itself has mass, which means you need additional fuel to accelerate the fuel, which adds more mass, which demands more fuel. The cycle spirals into absurdity long before you reach speeds relevant to crossing 1 light-year. Even advanced propulsion concepts like nuclear thermal or ion drives, which achieve much higher exhaust velocities than chemical rockets, eventually run into the same exponential wall. Nuclear thermal rockets achieve exhaust velocities of roughly 8 to 9 kilometers per second, about double that of chemical rockets. This helps enormously for missions within the solar system, cutting travel times to Mars by weeks and enabling faster trajectories to the outer planets. But doubling the exhaust velocity does not double the achievable speed in any simple way. Because of the exponential nature of the rocket equation, the improvement shifts the wall rather than removing it. A nuclear thermal rocket can reach higher speeds with practical fuel loads, but those speeds are still measured in tens of kilometers per second, not thousands. Still, solar system speeds, still millennia per light year. The speed gap is not just large, it is layered. Every attempt to close it encounters new obstacles at each level. Reaching Voyager speed is a solved problem, but gives you millennia per light year. Reaching 10 times Voyager speed requires fundamentally new propulsion and gives you centuries per light year. Reaching 100 times Voyager speed requires energy budgets that rival national power grids and gives you decades per light year. Reaching 1,000 times Voyager speed requires physics that humanity does not yet possess and still gives you years per light year. And at every step, increasing speed introduces new dangers that did not exist at lower velocities. Dangers that become clear the moment you try to go faster. Because crossing 1 light year is not just a problem of speed. It is a problem where going faster creates new problems that are themselves nearly unsolvable. The machines we have built are extraordinary. Voyager has operated for nearly half a century in conditions that would destroy any other human technology. Parker has survived temperatures that would melt steel, diving through the outer atmosphere of a star. New Horizons crossed the solar system faster than any mission before it and returned images of a world 3 billion miles from home. These are genuine achievements. They represent the peak of what human engineering can accomplish with chemical rockets, gravity assists, and decades of mission planning. But against the distance of 1 light year, they are almost motionless. 17 kilometers per second is fast enough to explore the solar system. It is fast enough to visit every planet, every dwarf planet, every moon and asteroid within our sun's domain. It is fast enough to escape the solar system entirely, as Voyager has proven, drifting outward into the interstellar medium with no way to return. What it is not fast enough to do is cross even 1 light year in any time frame that a human being, a human government, a human civilization, or even a human species could meaningfully plan around. The speed gap between our machines and the light year is so enormous that it converts a single unit of interstellar distance into a journey longer than the entire arc of human history. If 1 light year were a wall, our fastest spacecraft would be scratching at its base with a fingernail. The wall would not notice. But what if the fingernail could be replaced with something sharper? What if entirely new propulsion concepts could close a portion of that gap, pushing spacecraft to 1%, 5%, even 20% of light speed? Would 1 light year finally become crossable in a human lifetime? The answer involves numbers that should inspire hope, and engineering realities that immediately take that hope away. In April 2016, a group of scientists, engineers, and billionaires stood on a stage in New York City and announced the most ambitious propulsion concept in the history of spaceflight. The project was called Breakthrough Starshot. Its founder, the Israeli billionaire Yuri Milner, pledged $100 million. Stephen Hawking sat on the board. The goal was simple to state and almost impossible to achieve. Build a ground-based laser array capable of firing 100 gigawatts of focused light at a spacecraft the size of a postage stamp, equipped with a reflective sail a few meters wide, and accelerate that tiny craft to 20% of the speed of light in roughly 10 minutes. At that velocity, the spacecraft would cross 1 light year in 5 years. It would reach Proxima Centauri in about 20 years. Humanity would have its first interstellar probe. The concept was elegant in principle. The spacecraft, called a nanocraft, would carry no fuel. All of the energy for acceleration would come from the laser array on the ground. The craft itself would weigh about 1 gram, roughly the mass of a paperclip. A tiny silicon chip containing a camera, navigation system, and communication equipment would ride the beam of light like a leaf in a hurricane, accelerating from rest to 60,000 kilometers per second in the time it takes to cook a meal. For a few years, the project generated genuine scientific progress. Researchers investigated sail materials, laser coherence, thermal management, and targeting systems. Approximately 50 peer-reviewed papers emerged from the effort. Phase 1 of the program, intended to identify fundamental showstoppers in the physics, was largely completed. No absolute physical barrier to the concept was found. Then the funding dried up. By 2025, Breakthrough Starshot was placed on indefinite hold. Reports indicated that only about $4.5 million of the promised $100 million had been spent. The researchers involved heard informally that the project was done. No final announcement was made. The most ambitious interstellar propulsion concept ever funded had quietly disappeared, not because the physics was impossible, but because the engineering was too far from reality and the money stopped flowing. The concept remains valid on paper. A laser sail could theoretically accelerate a gram-scale craft to 20% of light speed, but building the laser array alone would require technology that does not exist yet, at a cost that would rival the budgets of major national space programs. This is important because Breakthrough Starshot was not a fantasy. It was the most credible near-term concept for reaching interstellar speeds. Its pause does not mean interstellar propulsion is abandoned forever, but it does mean that the only funded program targeting a meaningful fraction of light speed could not survive a single decade of development. The gap between concept and capability was too wide for private funding to bridge. Meanwhile, other propulsion technologies have faced their own reckonings. Nuclear thermal propulsion, which heats hydrogen fuel through a fission reactor to produce roughly double the efficiency of chemical rockets, was being developed by NASA and the Defense Advanced Research Projects Agency under a program called the Demonstration Rocket for Agile Cislunar Operations. The program aimed to test a nuclear thermal engine in space, with launch planned for 2027. Instead, the program was cancelled in 2026 after a reassessment concluded that other propulsion approaches were more cost-effective for the missions under consideration. NASA's fiscal year 2026 budget eliminated funding for both nuclear thermal and nuclear electric propulsion development. Nuclear thermal propulsion is real technology. It was successfully tested on the ground during the 1960s and 70s under a program called NERVA. Engines were built, fired, and shown to work. But even at peak performance, nuclear thermal rockets produce speeds useful for reaching Mars in weeks instead of months. They do not produce interstellar speeds. A nuclear thermal spacecraft could not reach 1% of light speed without carrying an impractical quantity of propellant. The technology is transformative for solar system exploration and irrelevant for crossing 1 light year in any human timeframe. Fusion propulsion, which would harness the same reactions that power the Sun, offers higher theoretical speeds. A fusion rocket could potentially achieve exhaust velocities of several thousand kilometers per second, enabling spacecraft speeds of perhaps 5 to 10% of light speed under optimistic assumptions. At 10% of light speed, 1 light year would take 10 years to cross. That sounds almost manageable, but fusion propulsion remains decades away from even a basic demonstration in space, and the engineering challenges involved in building a fusion reactor, light enough to fly and robust enough to operate for years without maintenance, are staggering. No fusion engine has ever been tested in space. No fusion engine has ever been built for spaceflight. The concept lives entirely in simulations and design studies. Ion drives, which accelerate charged particles to produce gentle but continuous thrust over long periods, have been used successfully on missions like Dawn and Deep Space One. They are exceptionally efficient, squeezing more velocity from each kilogram of fuel than any chemical rocket, but they produce tiny amounts of thrust. Accelerating a spacecraft to interstellar speeds using ion propulsion would require running the engines continuously for decades, consuming enormous quantities of electrical power that no current spacecraft power system can provide. Even the most advanced ion drives under development would struggle to push a craft beyond 1 or 2% of the speed of light, and the acceleration phase alone might take centuries. Every propulsion concept on the table either lacks the speed for interstellar travel or lacks the engineering maturity to be built. This is not pessimism, it is the current state of the technology. Chemical rockets are mature but too slow. Nuclear thermal is proven but still too slow. Ion drives are efficient but too weak. Fusion is fast enough in theory but decades from demonstration. Laser sails are fast enough in theory but lost their funding. The propulsion landscape in 2026 is wider than at any point in the space age, and none of it can currently cross 1 light year in a human lifetime. But suppose the engineering problems were solved. Suppose a future generation built a laser array powerful enough to push a nanocraft to 20% of light speed, or a fusion engine capable of sustaining 10%. Would the problem of crossing 1 light year be reduced to a simple matter of patience and flight time? No, because speed creates its own catastrophes. The first catastrophe is energy. Accelerating even a small object to a significant fraction of light speed requires amounts of energy that are difficult to comprehend. A spacecraft massing 1,000 kilograms, roughly the weight of a Voyager probe, accelerated to 20% of light speed, would carry approximately 1.8 times 10 to the 18th joules of kinetic energy. That number is abstract, so consider what it represents in terms you can feel. A large nuclear power plant produces roughly 8 gigawatts of electrical output. If you ran that plant at full capacity for 7 years and captured every single watt of energy it produced, converting nothing to waste heat, losing nothing to transmission, dedicating the entire output of the most powerful generating station ever built to a single purpose for nearly a decade, you would have just barely accumulated enough energy to accelerate 1,000 kilograms to 20% of light speed. One small probe, one act of acceleration, 7 years of the world's largest power plant, and that comparison is generous, because real energy systems lose enormous fractions of their output to inefficiency. Lasers convert electrical energy to coherent light at efficiencies far below 100%. The energy that misses the sail is wasted. The energy absorbed by the sail as heat rather than reflected as momentum is wasted. In practice, you would need several times more energy than the theoretical minimum, which means not one power plant for 7 years, but multiple power plants for decades. All for a spacecraft that weighs less than a small car. Global annual electricity production is roughly on the order of 10 to the 20th joules. The energy needed to push a single Voyager mass probe to 20% of light speed is approximately 2% of the entire world's yearly electrical output, all of it consumed in a single act of acceleration for a single spacecraft. Increase the mass, and the energy requirements become absurd. A crewed vessel, capable of supporting even a small crew for years, would mass thousands of tons at minimum. Once you include life support systems, food, water, shielding, structural materials, and the crew themselves, the energy required to accelerate thousands of tons to even 5% of light speed would exceed the total energy output of human civilization for an entire year. This is not an engineering limitation that better technology will solve. It is a consequence of physics. Kinetic energy scales with the square of velocity. Double the speed, quadruple the energy. Triple the speed, multiply the energy by 9. Approaching even modest fractions of light speed demands energy on a scale that dwarfs anything humanity currently produces. Breakthrough starshots sidestep this problem by making the spacecraft absurdly small. 1 gram, a paperclip. At that mass, the energy needed to reach 20% of light speed drops to a level that a powerful laser array could theoretically deliver in minutes. But a 1 gram spacecraft cannot carry humans. It cannot carry meaningful scientific instruments beyond a tiny camera. It cannot slow down at its destination because it carries no fuel and no engine. It would fly past its target star at 60,000 kilometers per second, snapping photographs during a flyby lasting only a few hours, then continue into the void forever. The entire concept depends on making the spacecraft so small that the energy problem becomes tractable. The moment you add mass, the energy budget detonates. But even if the energy existed, delivering it creates a separate constraint that rarely appears in public discussions of interstellar speed. The acceleration itself takes time, and the amount of time depends entirely on how hard you push. Breakthrough starshots solved this by applying a staggering force to a tiny mass. 100 gigawatts of laser power, concentrated on a 1 gram sail, produces an acceleration of thousands of times Earth's gravity. At that force, the nanocraft reaches 20% of light speed in roughly 10 minutes. This is survivable for a silicon chip. It is not survivable for a human being. The maximum sustained acceleration a trained human body can tolerate for extended periods is roughly 1.5 times Earth's gravity. Beyond that, blood pooling, vision impairment, and organ stress escalate rapidly. Long-term exposure to even moderate G-forces degrades the body in ways that mimic and compound the damage from microgravity. For a crewed spacecraft limited to 1 G of sustained acceleration, the time required to reach interstellar speeds becomes a significant portion of the journey itself. At 1 G of continuous thrust, a vessel would reach 20% of light speed in about 70 days. That sounds manageable, but 70 days of continuous uninterrupted engine burn is something no spacecraft has ever accomplished. Chemical rockets burn for minutes. The longest single burn of a conventional rocket engine lasted about 90 minutes. Ion drives can thrust for months at a time, but they produce accelerations thousands of times weaker than 1 G, far too gentle to reach interstellar speeds in any useful time frame. The paradox sharpens with realistic engines. An advanced ion drive might produce an acceleration of roughly 1/100th of a G. At that rate, reaching 10% of light speed would require approximately 10 years of continuous firing. 10 years during which the engine must operate every second of every day, without failure, without running out of propellant, without losing electrical power. A single interruption means the spacecraft reaches its coast phase at a lower speed than planned. A lower coast speed means a longer crossing time. A longer crossing means more time exposed to every other hazard the journey presents. At 1,000th of a G, a more realistic figure for current ion drive technology, reaching 10% of light speed would take roughly 97 years of continuous thrust. The acceleration phase alone would consume an entire human lifetime. The spacecraft would still be speeding up when the engineers who designed it had long since died. This creates a vicious trade-off. Gentle acceleration is kinder to the crew and requires lower thrust levels that are more achievable with near-term engines. But gentle acceleration stretches the burn time into decades or centuries, demanding an engine that can run continuously for longer than any machine in history has ever operated. Aggressive acceleration shortens the burn time, but requires forces that destroy human bodies or thrust levels that no existing engine can produce. There is no comfortable middle ground. Every combination of acceleration rate and target speed produces either an impossible engine requirement or an impossible human endurance requirement, often both. The second catastrophe is what happens to a spacecraft moving at high speed through interstellar space. The space between stars is not perfectly empty. It contains a thin haze of hydrogen gas, roughly 1 atom per cubic centimetre on average, along with occasional grains of interstellar dust. At Voyager speeds, this material is harmless. Individual atoms and microscopic dust particles bounce off or pass through the spacecraft without causing significant damage. At relativistic speeds, the situation transforms entirely. At 20% of light speed, every hydrogen atom that strikes the spacecraft's forward surface carries the kinetic energy of a fast-moving particle in a physics laboratory. The spacecraft is essentially flying through a particle beam of its own creation. The interstellar medium, usually so thin it barely qualifies as matter, becomes a continuous barrage of high-energy impacts. Research published by astrophysicists studying the breakthrough starshot concept found that at 20% of light speed, dust grain bombardment can erode approximately 0.5 millimeter of surface material from the leading edge of a spacecraft over the distance to Alpha Centauri. 0.5 millimeter may sound trivial, but for a sail only micrometers thick, it is annihilation. For a larger craft, the erosion accumulates over trillions of kilometers. Even a well-shielded vessel would need to account for continuous surface degradation across the entire journey. Larger dust grains, those massing even a fraction of a milligram, become far more dangerous. At 10% of light speed, a dust grain weighing 1 milligram carries kinetic energy equivalent to roughly 100 kilograms of high explosive. At 20% of light speed, the energy quadruples. A single grain would not merely puncture shielding, it would detonate against the hull like an artillery shell. And the spacecraft cannot dodge these particles because at those speeds, detection and maneuvering happen too slowly. By the time sensors register an incoming grain, the impact has already occurred. Shielding must be passive, heavy, and thick enough to absorb repeated strikes across years of flight. But dust erosion is only the mechanical threat. There is a separate and equally dangerous hazard that operates at the atomic level. At relativistic speeds, the stream of individual hydrogen atoms striking the forward hull does not merely erode the surface. Each atom arrives with enough kinetic energy to penetrate into the spacecraft's material, embedding itself in the molecular structure. Over trillions of impacts across years of flight, these implanted atoms accumulate. Hydrogen gas builds up inside the skin of the spacecraft at a specific depth determined by how far each atom penetrates before stopping. This is not a theoretical concern. It mirrors a well-studied problem in nuclear fusion research, where plasma-facing components inside fusion reactors are bombarded by hydrogen and helium ions. The implanted gas atoms form microscopic bubbles inside the material. As more gas accumulates, the bubbles grow, creating internal pressure that warps and weakens the surrounding structure. Eventually, the surface blisters. Blisters rupture. Layers of material peel away in a process called exfoliation. The spacecraft's own forward hull slowly destroys itself from the inside out, eaten by the hydrogen it is flying through. Researchers at NASA and affiliated laboratories have modeled this process for relativistic spacecraft and confirmed that it represents a serious threat. At 20% of light speed, the rate of hydrogen implantation is high enough that surface blistering could begin within the first fraction of the journey. Mitigation strategies exist in theory, such as using materials with high hydrogen diffusivity that allow the implanted atoms to migrate out before they accumulate, or designing sacrificial forward layers that can be jettisoned as they degrade. But every mitigation adds mass, complexity, and failure modes. And beyond the mechanical and chemical damage, there is radiation. The stream of hydrogen atoms striking the hull at 20% of light speed does not arrive gently. Each atom carries energy in the mega-electron-volt range, comparable to the particles used in medical radiation therapy. The forward face of the spacecraft becomes, in effect, a radiation source. The hull glows with secondary particles generated by each impact. X-rays, gamma rays, neutrons, cascading through the shielding material and into the interior of the craft. For a robotic probe carrying only electronics, this radiation degrades circuits, corrupts memory, and shortens component lifetimes. For a crewed vessel carrying biological tissue, it is potentially lethal. The radiation dose, accumulated over years of flight at 20% of light speed, through the average interstellar medium, could exceed the lifetime limits set for astronauts aboard the International Space Station within the first months of the journey. Shielding against this radiation is possible, but the shielding itself must be massive. Dense materials like tungsten or polyethylene can absorb and scatter incoming particles, reducing the dose to survivable levels. But adding tens or hundreds of tons of shielding to a spacecraft dramatically increases its mass, which circles back to the energy catastrophe. More mass requires more energy to accelerate. More energy requires larger propulsion systems. Larger systems mean more mass. The cycle feeds on itself. For a gram-scale nanocraft with no shielding at all, the survival strategy is different. You launch thousands of them and accept that many will be destroyed during the journey. The ones that survive deliver data. This is a viable approach for tiny expendable probes. It is not a viable approach for a crewed vessel carrying irreplaceable human lives. The third catastrophe is one that science fiction has taught most people to misunderstand: time dilation. Einstein's theory of special relativity predicts that time passes more slowly for objects moving at high speeds relative to a stationary observer. This effect is real, confirmed by countless experiments, and it applies to any spacecraft traveling at a significant fraction of light speed. At 20% of light speed, the effect is measurable but modest. The time dilation factor, calculated from the mathematics of special relativity, is approximately 1.02. This means that for every year that passes on Earth, roughly 11 months and 3 weeks pass aboard the spacecraft. The crew ages slightly less than the people they left behind. Over a 20-year journey to Proxima Centauri, the total time saved by dilation would be only a few months. Noticeable to a physicist, irrelevant to a mission planner. Even at 50% of light speed, the dilation factor is only about 1.15. A 20-year journey would feel like roughly 17.5 years to the crew. Meaningful but not transformative. The science fiction fantasy of relativistic travelers returning to Earth centuries after they left while having aged only a few years requires speeds far closer to light speed than any realistic propulsion concept can achieve. At 90% of light speed, the dilation factor reaches about 2.3, meaning a 10-year journey would feel like about 4.5 years. At 99%, the factor reaches roughly 7. But these speeds demand energy beyond anything conceivable with any technology humanity has imagined, including antimatter propulsion. Time dilation is real. It is not a solution. For any speed achievable by proposed propulsion technology, the time saved by relativistic effects is negligible compared to the journey duration. The crew will experience nearly the full passage of every year they spend in transit. There is no physics shortcut that makes 1 light year feel shorter from inside the spacecraft. The fourth catastrophe is deceleration. Every discussion of interstellar speed focuses on how fast you can go. Almost nobody talks about how you stop. A spacecraft that accelerates to 20% of light speed and does not slow down will blast past its target in hours. To actually enter orbit around another star, or even to conduct a slow flyby that allows meaningful observation, the spacecraft must shed its velocity. And decelerating from 20% of light speed requires exactly as much energy as accelerating to it in the first place. For a laser sail, deceleration is an unsolved problem. The laser array is on Earth, or in Earth orbit. It can push the sail away, but it cannot pull it back. Once the nanocraft is light years from the laser, no beam can reach it with enough intensity to slow it down. Some researchers have proposed using the target star's own light to decelerate, deploying the sail so that starlight provides a braking force. This is theoretically possible but requires precise engineering and dramatically extends the mission timeline. It also only works if the target star is bright enough, which Proxima Centauri, a dim red dwarf, may not be. For a craft using onboard fuel, deceleration doubles the total fuel requirement. You need fuel to speed up and fuel to slow down. But the fuel for deceleration must itself be accelerated during the first phase, which means you need additional fuel to carry the deceleration fuel. This is the tyranny of the rocket equation, the same mathematical relationship that punishes every additional kilometer per second of speed with exponentially more fuel mass. For interstellar missions at significant fractions of light speed, the rocket equation produces mass ratios so extreme that the required fuel mass exceeds the mass of any object humans could plausibly build. A fusion-powered spacecraft designed to accelerate to 10% of light speed and then decelerate at the destination would need a mass ratio of roughly 160,000 to 1. For every kilogram of payload that arrives, 160,000 kilograms of fuel must be loaded at departure. No material science, no engineering breakthrough, and no optimization can escape this fundamental mathematical constraint. The fifth catastrophe is the most devastating, and it only applies when humans are aboard. Everything described so far, the energy, the acceleration duration, the dust, the radiation, the deceleration, applies to robotic probes. Small machines that do not eat, do not breathe, do not age, do not panic, and do not care whether the journey takes 10 years or 10,000. A robotic probe can be miniaturized to reduce energy costs. It can be hardened to survive dust impacts. It can fly past its target without decelerating and still return useful data during a brief flyby window. Humans change every calculation. A crewed interstellar vessel must carry air, water, food, and fuel for recycling systems that keep all three available for the duration of the journey. It must carry medical facilities. It must carry radiation shielding massive enough to protect biological tissue from cosmic rays and the particle bombardment created by high-speed travel through the interstellar medium. It must maintain stable temperatures, pressures, and humidity levels within tolerances that keep human bodies functioning. It must provide enough space for crew members to move, exercise, and maintain psychological health across years or decades of confinement. But the biological costs run far deeper than life support logistics. The human body evolved for one specific gravitational environment and fails systematically when that environment is removed. Astronauts aboard the International Space Station lose approximately 1 to 2% of their bone mineral density per month in microgravity. Muscles atrophy. Fluid redistributes toward the head, increasing intracranial pressure and damaging vision. The cardiovascular system decalibrates, weakening the heart because it no longer needs to pump blood against full gravity. After 6 months in space, astronauts returning to Earth require weeks of rehabilitation to walk normally. After a year, some effects become partially irreversible. An interstellar journey lasting a decade or more would expose the crew to these degenerative processes for periods far exceeding anything the International Space Station has tested. Even with rigorous exercise protocols, which currently occupy roughly 2 hours of every astronaut's day aboard the station, the long-term degradation of bone and muscle in microgravity compounds year after year. Artificial gravity, created by rotating all or part of the spacecraft, could mitigate these problems, but it adds enormous structural mass and engineering complexity to a vessel that is already impossibly heavy. Cosmic ray exposure presents another biological threat that cannot be fully shielded against without prohibitive mass penalties. High-energy particles from distant supernovae and galactic sources penetrate spacecraft hulls and pass through human tissue, breaking strands of DNA and damaging cells. On Earth, the atmosphere and magnetic field absorb most of this radiation. In deep space, there is no such protection. Astronauts aboard the International Space Station, still partially shielded by Earth's magnetosphere, receive radiation doses roughly 100 times higher than the average person on the ground. An interstellar crew beyond any planetary magnetic field would receive substantially more. Over a decade, the cumulative dose could significantly increase cancer risk, accelerate aging, and cause cognitive decline. The effects on reproductive cells raise questions about whether crew members could safely bear children during or after the journey. And then there is the weight of isolation itself. No human being, has ever experienced the psychological conditions of interstellar flight. The longest continuous spaceflight on record lasted roughly 14 months aboard the Russian station Mir. Submarine deployments, Antarctic winter-over expeditions, and simulated Mars missions have tested isolation for periods of months to a year in controlled conditions on Earth. Interstellar travel would demand psychological endurance across decades, in an environment where the nearest possible rescue is years away at light speed and centuries away by any spacecraft that could physically reach you. The crew would watch Earth's sun fade to an unremarkable point among millions. They would know that everyone they left behind is aging faster than relativity allows them to perceive. They would exist in a closed social system with no possibility of new arrivals, no fresh perspectives, no escape from interpersonal conflict except the walls of a vessel they cannot leave. The mass of such a vessel dwarfs anything humanity has launched into space. The International Space Station, the largest structure humans have ever assembled in orbit, masses approximately 420 metric tons and supports a crew of 6 for months at a time while receiving regular supply shipments from Earth. An interstellar vessel would need to be entirely self-sufficient. No resupply missions, no repair crews sent from home. Every system must work for the entire duration of the journey or be repairable using only materials carried aboard. And this requirement of total self-sufficiency exposes a problem that cuts across every design, whether robotic or crewed, whether lasting a decade or a century. No machine humanity has ever built has operated continuously without external maintenance for more than roughly 50 years, and the machines that have lasted that long are dying. Voyager 1 is the proof. After 49 years, its radioisotope power source has decayed to the point where instruments must be shut down one by one to keep any of them running. Seals have degraded, heaters have failed, memory chips have corrupted. In 2023, a fault in one of the flight data computers caused the spacecraft to transmit garbled data for months before engineers devised a workaround across a 24-hour communication delay. The workaround involved writing new software to route around a damaged memory chip. The fix worked, but it required the ingenuity of an entire ground team on Earth, a luxury that a spacecraft 1 light-year from home would not have. The International Space Station requires constant maintenance. Astronauts spend a significant fraction of their working hours repairing systems, replacing components, and troubleshooting failures. Pumps fail, cooling lines leak, solar panels degrade, computer systems crash, and the station receives regular resupply missions that deliver replacement parts manufactured by industries on Earth. Strip away those supply lines and that ground support, and the station would become uninhabitable within months. An interstellar spacecraft must carry every spare part it will ever need, every replacement pump, every backup circuit board, every tube of sealant, every meter of replacement wiring. It must carry the tools to install those parts and the diagnostic equipment to identify which parts need replacing. For a 10-year journey, every component must either last 10 years without failure or be replaceable from onboard stores. For a 100-year journey, every component must last a century or be manufactured aboard the vessel from raw materials. No supply chain exists. No factory stands ready to produce a replacement for a part that was not anticipated to fail. Bearings wear, seals degrade, lubricants evaporate in vacuum, metals fatigue under cyclic stress. Radiation damages electronics, accumulating errors in memory and logic circuits over years. Software drifts, accumulating bugs, and unintended interactions between systems that were never tested for decade-long continuous operation. Every mechanical, electronic, and software system aboard the vessel faces failure modes that intensify with time. Redundancy helps. Carrying backup systems for every critical function extends the window before failure becomes fatal. But redundancy does not eliminate the problem, it delays it. And delay is not enough when the journey itself lasts longer than any machine in history has operated, without human hands reaching in from outside to fix it. This is the longevity wall. It is separate from the energy problem, the speed problem, the shielding problem, and the crew survival problem. It applies to every interstellar vessel regardless of design. A robotic probe carrying no humans still needs its communication system to function for the full journey, its navigation sensors to remain calibrated, its data storage to remain intact. A crewed vessel needs everything. A robotic probe needs plus everything required to keep human beings alive. And every additional system is another point of failure that must endure for years or decades without external support. Conservative estimates for a minimal crewed interstellar vessel, carrying perhaps 10 to 20 people with enough supplies and redundancy for a decade-long journey, place the total mass in the range of thousands to tens of thousands of metric tons. Accelerating 10,000 metric tons to even 5% of light speed would require energy equivalent to the total output of human civilization for multiple years, channeled entirely into a single vehicle. The engineering does not exist. The energy infrastructure does not exist. The materials science does not exist. No component of this system is close to being buildable with current or near-future technology. Some thinkers have proposed sidestepping the problem of journey duration by building vessels so large and self-sustaining that multiple generations could live and die aboard them during the crossing. These generation ships, as they are called, would function as miniature worlds, carrying not just a crew but an entire self-reproducing community. Farms would grow food, factories would manufacture replacement parts, children would be born, raised and educated aboard the ship, knowing no other home. Their grandchildren, or their grandchildren's grandchildren, would eventually arrive at the destination. The concept sounds elegant in the way that many interstellar ideas sound elegant from a distance. Up close, it dissolves into catastrophe. A generation ship must sustain a population large enough to avoid genetic bottleneck. If the founding population is too small, inbreeding over multiple generations leads to reduced genetic diversity, increased susceptibility to disease, and declining health across the entire community. Geneticists estimate that a minimum viable population for long-term multi-generational survival requires at least several hundred individuals, and more conservative estimates suggest several thousand. A ship carrying thousands of people, with all the food, water, air, living space, agricultural systems, medical facilities, educational infrastructure, and social institutions necessary to sustain a functioning community for centuries, would mass not thousands of metric tons, but potentially millions. Even setting aside the mass, the social engineering challenges are staggering. No human community has ever maintained stable governance across centuries without external contact. Civilizations on Earth with access to new ideas, trade, migration, and natural resources routinely collapse, fracture, or transform beyond recognition within a few hundred years. A generation ship offers none of these stabilizing forces. The community is sealed, resources are finite, there is no outside world to trade with, no frontier to expand into, no neighboring culture to absorb. The social dynamics of a closed system under those conditions are unstudied because nothing equivalent has ever existed. And at the core of the generation ship concept lies an ethical question that has no comfortable answer. The people who choose to board the ship volunteer. Their children do not. Their grandchildren do not. Generation after generation would be born into a vessel they never chose, pursuing a destination they will never see, inheriting a mission that was decided for them by ancestors they may or may not revere. The arrival generation, if the ship survives, would be culturally, linguistically, and perhaps genetically distinct from the departure generation. They would step onto an alien world carrying a mandate from people who have been dead for centuries. Whether they honour that mandate or reject it is a question no mission planner can answer in advance. At 1 light year from Earth, a radio signal travelling at light speed takes 1 full year to reach home. A message sent from the spacecraft would not receive a reply for 2 years. At 4 light years from Earth, the round-trip communication delay stretches to nearly 9 years. The crew or the community would be functionally alone, unable to consult with mission control in real time, unable to receive emergency guidance, unable to even confirm that Earth still existed and was listening. Every decision, every crisis, every malfunction would have to be handled independently by people sealed inside a vessel hurtling through emptiness at speeds that make rescue impossible. This is the divide that 1 light year exposes with surgical precision. For a gram-scale robotic chip, 1 light year is a 5-year flight at 20% of light speed, assuming the engineering challenges of laser propulsion are eventually solved. Difficult, expensive, but perhaps achievable within a century or two of sustained development. For a crewed vessel, 1 light year is a journey that demands energy humanity cannot yet produce. shielding humanity cannot yet build, life support humanity cannot yet sustain, and psychological endurance humanity has never tested. The distance is the same. The experience of crossing it is separated by an abyss. 1 light-year does not scale politely between probes and people. It transforms. For a machine, it is a hard engineering problem. For a human being, it is an almost complete reimagining of what a journey means. Not a trip with a departure and an arrival, but a commitment that reshapes an entire life, or multiple generations of lives, around the single act of crossing a distance that light handles in 12 months and human technology handles in millennia. The propulsion concepts are real. The physics permits speeds that would reduce crossing times from thousands of years to mere decades. But every step toward faster travel summons new obstacles that grow as fast as the solutions. Energy demands multiply. The acceleration phase stretches into years. Interstellar hazards intensify. Radiation saturates the hull. The mass penalty of carrying human passengers overwhelms every propulsion advantage. The communication delay severs the crew from everything and everyone they have ever known. The human body, evolved for the savannas of East Africa, quietly falls apart in the environment that interstellar travel demands, and every mechanical system aboard the vessel ticks steadily toward failure, with no repair dock waiting at the other end. Even if every one of these barriers were overcome, even if a future civilization built a fusion-powered, heavily shielded, artificially gravitied, fully self-sufficient vessel capable of carrying humans across 1 light-year in a decade, the accomplishment would represent the most extreme engineering challenge ever undertaken by any species on Earth. Not an extension of current spaceflight, not a logical next step beyond Mars or the outer planets. A fundamentally different kind of achievement, belonging to a fundamentally different kind of civilization. And that single light-year would still be less than a quarter of the way to the nearest star. What remains is the question of what this distance truly represents. Not as an engineering challenge, not as a number on a chart, but as a statement about where humanity stands on the threshold between a planetary species and an interstellar one. There is nothing 1 light-year away. This is the detail that almost never appears in conversations about interstellar distance, and it changes the meaning of everything discussed so far. 1 light-year is not a destination. No star sits at that distance from our sun. No planet orbits there. No landmark, no waypoint, no useful object of any kind marks the spot where 1 light-year ends. If you travelled 1 light-year from Earth in any direction, you would arrive at a point in space indistinguishable from the emptiness you had been crossing for the entire journey. The same sparse hydrogen atoms, the same faint cosmic radiation, the same absolute darkness in every direction, broken only by the fixed, cold light of distant stars that appear no closer than when you started. 1 light-year is not a place. It is a unit of measurement, a mark on a ruler, and the ruler itself stretches across distances so enormous that 1 light-year is the smallest division that astronomers find useful when describing the gaps between stars. It is the centimetre on a tape measure designed for surveying continents. Using it to describe interstellar distances is already an act of compression, a way of making the incomprehensible slightly less overwhelming by packaging it into manageable units. But the units themselves are not manageable. Each one contains 9.46 trillion kilometres of vacuum, and the nearest star requires more than 4 of them laid end to end. Proxima Centauri, the closest known star to our Sun, sits 4.24 light-years away. Crossing 1 light-year in the direction of Proxima Centauri would leave you stranded in open space with more than 3 light-years still to travel. You would have completed less than a quarter of the shortest possible interstellar journey, and there would be no way to refuel, resupply, or turn back. The sun behind you would be dimmer than the brightest stars in the night sky of Earth. Proxima Centauri ahead of you would still be a faint red point, barely distinguishable from the stellar background. You would occupy a region of space that belongs to no star, no system, no gravitational neighbourhood. A region that exists only as distance, pure and featureless. The next nearest stars are not much closer to the 1 light-year mark. Barnard's star sits roughly 6 light-years from Earth. The binary system of Lumen 16 is approximately 6.5. Wolf 359 is nearly 8. Sirius, the brightest star in the night sky, is 8.6 light-years away. These are our closest cosmic neighbors, and every single one of them requires multiple light years to reach. 1 light year does not get you to any of them. It does not get you close to any of them. It gets you into the space between, the void that separates all stars from all other stars, a void so thorough that it contains essentially nothing and leads essentially nowhere. This is what makes 1 light year so much more frightening than its modest-sounding name suggests. It is not the distance to a goal, it is the distance that proves how far away every goal actually is. Crossing it does not bring you closer to the stars in any way that would feel meaningful to a human being aboard a spacecraft. It brings you only to the realization that interstellar space is not a place you pass through on the way to something else. It is the thing itself. The overwhelming majority of every interstellar journey is emptiness, and 1 light year is the unit that measures how much emptiness there is. Now reassemble everything the journey through this distance has revealed, and examine what 1 light year actually means. At current spacecraft speeds, crossing 1 light year takes approximately 17,600 years. This means that a journey to even the nearest star, requiring more than 4 light years, would take roughly 75,000 years using the fastest outward-bound technology humanity possesses. 75,000 years ago, modern humans were only beginning to migrate out of Africa. The entire history of human civilization, from the first permanent settlements through the invention of agriculture, through the Industrial Revolution, through the space age, occupies less than 1/10 of that time span. Reaching the nearest star at Voyager's speed would require a duration longer than the period separating us from the cave painters of Lascaux. It would require a commitment of time so vast that the civilization launching the mission and the civilization receiving its results could not plausibly be the same species. At proposed future speeds, the picture changes but does not resolve. A laser-driven nanocraft, travelling at 20% of light speed, could cross 1 light year in 5 years and reach Proxima Centauri in about 20. A fusion-powered vessel at 10% of light speed could manage the same crossing in 10 years and arrive at Proxima Centauri in roughly 42. These numbers sound achievable. They fit within a human lifespan. They suggest that 1 light year might eventually be crossable by machines that humans alive today could design. But the engineering required to reach those speeds does not yet exist. The most ambitious funded program targeting interstellar velocities was paused indefinitely in 2025 after less than a decade of work and a fraction of its promised budget. Nuclear thermal propulsion, the nearest term advanced engine, was defunded in 2026 and would not have been fast enough for interstellar travel regardless. Fusion propulsion remains a laboratory concept with no spaceflight demonstration on any timeline. Every pathway to closing the speed gap between current technology and the light year is either unfunded, undeveloped, or both. And even when speed increases, it does not simplify the problem. It transforms the problem. The energy required to accelerate even a small probe to 20% of light speed rivals a significant fraction of global energy production. Interstellar dust becomes a destructive force at relativistic velocities, threatening to erode or puncture any craft that lacks heavy shielding. Deceleration at the destination demands a second energy expenditure equal to the first, and no laser sail solution for braking has been demonstrated. Communication delays stretch to years, severing any real-time link between crew and home. For a robotic probe, these problems are severe, but potentially solvable across decades of development. For a crewed mission, they become almost insurmountable. The mass of a crewed vessel amplifies every energy requirement by orders of magnitude. Life support systems must function without failure for years or decades. Radiation shielding must protect biological tissue from cosmic rays and relativistic hydrogen impacts. The psychological endurance required of a crew confined to a vessel for decades, cut off from Earth by communication delays measured in years, exceeds anything human beings have ever been asked to sustain. 1 light year reveals all of this. It does not create these problems. They exist as consequences of physics, engineering, and biology. But 1 light year is the distance at which they first become visible. Within the solar system, none of these barriers matter. You can reach Mars in months using chemical rockets. You can reach Jupiter in years. Even the outer planets, billions of kilometers away, are accessible using gravity assists and patient coasting. The solar system is vast, but it is traversable with technology that exists today. 1 light-year is where that traversability ends. The gap between the farthest distance humanity has traveled and the distance of 1 light-year is not a slope, it is a cliff. Voyager 1, after nearly 50 years of flight, has covered less than 3,000ths of a light-year. Scaling from Voyager's achievement to 1 light-year requires multiplying every aspect of the mission, its duration, its energy, its engineering endurance, by a factor of several hundred. Scaling from 1 light-year to the nearest star requires multiplying again by more than 4. And scaling from the nearest star to the broader galaxy requires multiplying by thousands, then millions. Each multiplication does not simply add difficulty, it changes the nature of the problem. Crossing the solar system is a navigation problem. Crossing 1 light-year is an energy problem. Crossing 4 light-years is a survival problem. Crossing 1,000 light-years would be a civilization problem, demanding infrastructure, governance, and continuity on scales that no human society has ever maintained. The light-year does not just measure distance, it measures the escalation of difficulty at each threshold of cosmic scale. And the first threshold, the one that separates planetary civilization from interstellar ambition, is 1 light-year. This is why 1 light-year matters so much more than its numerical smallness suggests. It is not the distance to a star, it is the distance at which travel itself changes its fundamental character. Within the solar system, a journey is something that begins, proceeds, and ends within a single human context. You launch a probe, you monitor its progress, you receive its data. The people who design the mission are alive when the results arrive. The institutions that funded it still exist. The technology that built it is still understood. The journey fits within the temporal and organizational boundaries of a single civilization. 1 light-year shatters those boundaries. Even at speeds 10 times faster than Voyager, crossing 1 light-year takes roughly 1,760 years. At speeds 100 times faster, it still takes 176 years. Only at speeds more than 1,000 times faster than current technology, speeds that represent several percent of light speed, does the crossing time fall within a single extended human lifespan. And achieving those speeds demands capabilities so far beyond what humans currently possess that they belong to a civilization we cannot yet imagine. This is the deepest truth that 1 light-year contains. It is not a measure of distance in the ordinary sense. It is a measure of the gap between the kind of civilization we are and the kind of civilization we would need to become. Crossing 1 light-year requires not just faster engines or bigger fuel tanks. It requires energy production on a planetary scale, material science capable of withstanding relativistic bombardment, propulsion technology decades or centuries beyond current prototypes, and either robotic autonomy sophisticated enough to conduct a mission without human oversight or crude spaceflight endurance, exceeding anything humans have ever attempted. No single breakthrough delivers all of these capabilities. They must emerge together, reinforcing each other across multiple generations of sustained development, maintained by institutions stable enough to persist across centuries of effort. Try to picture what such a civilization would look like, not in the abstract language of physics papers, but as a living society organized around the goal of crossing interstellar distance. It would need energy infrastructure spanning continents, dedicated for decades to charging the propulsion systems of a single vessel or powering the laser arrays that would push a fleet of sails toward the stars. It would need mining operations across the solar system, harvesting materials from asteroids and moons to build shielding, fuel containment, and structural components too massive to lift economically from Earth's surface. It would need educational systems that train generations of engineers and scientists, not for careers that end in retirement, but for careers that hand their work to successors who hand it to their own successors, each generation advancing a design that none of them will see completed. It would need governance structures capable of maintaining funding, focus, and public support across political cycles, across economic downturns, across wars and cultural upheavals, across the rise and fall of ideologies that have not yet been imagined. It would need to treat the interstellar mission not as a project within a civilization, but as the organizing purpose of the civilization itself. The way cathedral cities in medieval Europe oriented entire economies around structures that took longer to build than any individual craftsman lived. The difference is that a cathedral served the community that built it. An interstellar mission serves descendants who may not share the values, the language, or even the biological form of the people who began it. The civilization that crosses 1 light year would need to accept, as a foundational commitment, that it is building something whose completion it will never witness, and whose beneficiaries it will never know. This is not how human societies have ever organized themselves. Civilizations build for their children, occasionally for their grandchildren. They do not build for strangers separated from them by centuries of cultural drift. The interstellar project demands exactly that. A commitment to the distant future so absolute that it functions more like a religious covenant than an engineering program. Not faith in a deity, but faith in continuity itself. Faith that the institutions will hold. Faith that the knowledge will transmit. Faith that the mission will be inherited by people who choose to continue what was started before they were born. Humanity has never sustained a single engineering project for more than a few decades. The longest-running space missions, the Voyagers, are approaching 50 years and are nearly dead. The longest-running scientific institutions are a few centuries old. The longest-running continuous civilizations have histories measured in thousands of years, but none of them have maintained a single technological objective across that entire span. Crossing 1 light year demands continuity on a scale that human institutions have never demonstrated. It demands that a civilization choose a goal and pursue it across timescales longer than most nations survive. This does not mean it is impossible. It means it belongs to a different category of achievement than anything humanity has yet accomplished. Building the pyramids required organizing thousands of workers for decades. Landing on the moon required mobilizing a nation's scientific infrastructure for less than 10 years. Crossing 1 light year would require mobilizing a civilization's total capability for generations, directing a significant fraction of its energy production toward a single objective, and maintaining that commitment through political upheavals, economic crises, wars, and cultural transformations that cannot be predicted. The light year does not say no, it says not yet, and it says not easily, and it says not with anything resembling the technology, the energy infrastructure, or the institutional endurance that currently exists on Earth. 1 light year is a filter. On one side sit planetary species, creatures that have mastered the distances within their own star system, that have sent machines to neighboring worlds and beamed signals across billions of kilometers. On the other side sit interstellar species, civilizations that have crossed the gap between stars and can think in terms of light years the way planetary species think in terms of kilometers. The filter between them is 1 light year, the smallest useful unit of interstellar distance, and it is almost impossibly wide. Every few years, someone proposes a new concept that sounds like it might close the gap. Warp drives that bend space, antimatter engines that convert mass directly to energy, enormous solar sails that catch starlight across millions of square meters of reflective surface. Each concept has its own physics, its own plausibility spectrum, its own set of enthusiasts who believe it could work within a century. None of them have been built. None of them have been demonstrated. Some of them may violate physical laws that we do not yet fully understand. The history of interstellar propulsion concepts is a history of brilliant ideas that remain, for now, ideas. But the ideas keep coming, and the physics behind some of them is sound. Laser sails work, the photons carry momentum, the momentum transfers to the sail accelerates. Nothing in the laws of physics forbids this process from reaching 20% of light speed. The engineering is immature, the costs are extraordinary, and the institutional commitment required to develop the technology does not yet exist. But the physics permits it, and if the physics permits it, then the question is not whether it can happen, but when, and whether humanity will maintain the coherence necessary to pursue it long enough to succeed. This is what 1 light year ultimately asks of us. Not whether we are smart enough, not whether we are brave enough, whether we are patient enough, whether we can sustain a purpose across centuries, whether we can build institutions that outlive their founders and technologies that outlive their inventors, whether we can commit to a project so vast that the people who finish it will share nothing with the people who started it except the goal itself. 1 light year sits between the Earth and the stars like a question addressed to the entire species. It does not ask whether human beings can build faster engines. It asks whether human civilization can become something durable enough, coherent enough, and ambitious enough to match the distance that the universe places between every star and every other star. The terrifying truth is not that the stars are far away. People have known that for centuries. The terrifying truth is that 1 light year, the smallest meaningful distance between them, is already enough to expose every limitation of every machine, every energy system, and every institution that human civilization has ever created. Before humanity can dream of crossing the galaxy, before it can plan voyages to distant star systems, before it can even begin to think of itself as a spacefaring civilization in any interstellar sense, it must first confront the staggering scale hidden inside this single, deceptively small number. 1 light year, 9.46 trillion kilometers, 63,000 astronomical units. A distance that light crosses in a single year, and that the fastest human spacecraft would need 17,600 years to match. A distance so vast it may not even get you out of our own sun's gravitational influence. A distance that covers less than a quarter of the trip to the nearest star. A distance that demands energy, speed, endurance, and institutional commitment beyond anything that exists on Earth today. Not impossible, not forbidden by physics, not permanently beyond reach, but so far beyond the current reach of every technology and every institution on this planet that crossing it would require becoming a different kind of civilization entirely. 1 light year is not the distance to the stars. It is the distance to the beginning of the question of whether we will ever reach them, and even that beginning is almost more than we can cross.